Okay, so you have you got C, the capacitance equivalent to 240 microfarad for the star connection. Okay, for the delta connection, okay, so delta connection, V phase equivalent to V line to line. So here is 400 volt squared divided by 3.989 kVAR. Then you can get 40.1 ohms for the reactance. And then you calculate the capacitance is 1 over 2 pi times frequency times with the XC. Then you can get 79.4 microfarad. This one for the delta connection. Okay, so this is the practical power factor corrections league table that normally used by the industrial to get what is the value of the QC. So QC, the Q1 is before power factor correction and Q2 is after power factor correction. Okay, so we look onto the effective reactive power. So differences in voltage level between the supply system, okay, Vs, and also the capacitor, Vc, used will produce different injected reactive power into the system. So the factor to be considered is the by using the equation 4.11, Q capacitance equivalent to Qs supply times with the V capacitance divided by V supply squared. So where Q cap is the effective reactive power provided by the capacitor, Qs is the effective reactive power injected into supply system, V cap is the capacitor voltage level, and Vs is the supply system voltage level. So we look at example 3. If the capacitor of 525 volt is chosen as the power factor correction component in examples 1 and 2, determine the effective reactive power so that the overall system power factor can be improved to 0.9 lagging. Okay, so given that the V of the capacitor. So before this, there's no value for the V of the capacitor. Okay, so you use the previous equation, which is QC equivalent to QS times VC over VS squared, where VC is a V capacitance and VS is a V supply. Then you key in QS equivalent to 11.99 kVAR. Okay, times with the 525 volt divide 400 volt squared, then you can get 20.61 kVAR. Okay, that is the effective reactive power that can be used to correct the power factor to 0.9. Okay, next section is about harmonics in power system. So if we refer to the IEEE standard, a sinusoidal, this harmonics is a sinusoidal component of periodic wave or quantity having a frequency that is an integral multiple of the fundamental frequency. And then from the French mathematicians Jean-Baptiste Fourier, a periodic non-sinusoidal function of a fundamental frequency f may be expressed as the sum of sinusoidal functions of frequencies which are multiples of the fundamental frequency. Okay, so harmonics is the voltage or current at a multiple of the fundamental frequency system. So in power system, there are two types of harmonics, which are the voltage and current. Okay, so in a normal alternating current power system, the current varies sinusoidally at a specific frequency, usually 50 Hz. Okay, so this is the explanation on what is the current harmonics. Okay, when a linear electrical load such as rectifier, computers, printers connected to the system, so it withdraws not necessarily sinusoidal current at the same frequency as the voltage, but not in phase with the voltage. So the current waveform distortion can be quite complex depending on the type of load and its interaction with other components of the system. Okay, this is the what we call current harmonics. So voltage harmonics are mostly caused by the current harmonics. The voltage provided by the voltage source will be distorted by the current harmonics due to source impedance. So if the source impedance of the voltage source is small, so the current harmonics will cause only small voltage harmonics. Okay, that is the difference between the voltage and the current harmonics. So harmonics classification, you can see from this diagram. So first we have the subharmonics, okay? The subharmonics, the FH is less than F, okay? So FH is the harmonic frequency and F is the fundamental frequency. And then we can see here we have the integer or the characteristic harmonics. Okay, this one and this one is the characteristic harmonics or integer. So F for this characteristic is FH equivalent to NF. Okay, so N is the integer. Then we have the non-integer or the non-characteristic harmonics. Okay, so this characteristic is FH will bigger than F, okay, and FH is not equivalent with NF. So this is the characteristic of the harmonics in power system. Okay, here is the a sinusoidal voltage or the current function that is dependent on time t may be represented by the following expression. So this one, so the first one is the voltage function. This one is the voltage function. Okay, and then the second one is the current function. Okay, so this equation will reflect to this waveform. So this figure shows the sinusoidal voltage and current functions of the time. Okay, and then the presence of the harmonic components in the normal sinusoidal waveform produce a periodic non-sinusoidal waveform. Okay, you can see here it's not a non-sinusoidal, not a sinusoidal. So basically this is a sinusoidal. This one is non-sinusoidal. Okay, because of the interruption of the harmonics. Okay, and then this is the simplified Fourier expression to indicates the presence of the harmonic components in the normal sinusoidal waveform. So this figure shows the non-sinusoidal voltage waveform Fourier series. The Fourier series allows expression of non-sinusoidal periodic waveform in terms of sinusoidal harmonic frequency components. Okay. So this is the waveform of the creation of non-linear waveform by adding the fundamental and also the third harmonic frequency waveforms. Okay. So actually, if you refer to this equation, we have this one is the voltage output, this one is the fundamental, okay. This one is the fundamental voltage, this one is the voltage for the second harmonic, voltage for the third harmonic, and end harmonic. Okay, so this one is for the third harmonic. Okay, the Fourier series is simplified to express the periodic waveform, voltage waveform with fundamental frequency, which is omega equivalent to 2 pi f. Okay, so we can use equation 4.15 to get the voltage, to express the periodic voltage waveform. Okay, where AK and BK are the coefficient of the individual harmonic components. So this AK is here. This is the equivalent. Equivalent 4.16 is for the AK, and then BK, the equivalent is here. Okay, equation 4.17. So and then harmonics measurement indices. So how we want to measure this harmonic is by calculating the individual harmonic distortion IHD or the total harmonic distortion THD. So ratio if the IHD, individual harmonic distortion, is the ratio between the root mean square RMS value of the individual harmonic, okay, and the RMS value of the fundamental, which is IHDN, equivalent to IHDN equivalent to IN over I1 times with 100%. This one is equation 4.18. And then you can also calculate the total harmonic distortion or THD. So the ratio between the RMS value of the harmonics and the RMS value of the fundamental. So THD equivalent to summation of IN squared divided by I1 times 100%. So N is the integer 2, 3, 4 and until infinite. So this is equation 4.19. Okay, this is the root of the sum of the squares RSS and the THD of the bus voltage. So this is some of the example of the values for the harmonics. Harmonics order, the frequency. This is the impedance of the system 0.003 plus J2 pi F 30 microhenry ohms. Okay. And then you can know the frequency at 250, 350 Hertz, what is the harmonic order and what is the line current magnitude. Okay, and then this is all the value at the frequency, both frequency for the resistance, the impedance, the reactance, the current and also the voltage. Okay. Harmonic sources in electrical system. Many nonlinear loads drawing non-sinusoidal currents from the electrical power system. So basically nonlinear loads is something that have many types of implementation or application of the power electronic components. Okay, for example is rectifier, inverter, and so on. Okay, so these nonlinear loads will draw the non-sinusoidal currents from the electrical power system. So these non-sinusoidal currents pass through different impedances in the power system and it will produce the voltage harmonics. Okay, so these voltage harmonics propagate in power system and affect all the power system components. Okay, some of the harmonic sources in electrical systems, such as the fluorescent lighting. So fluorescent lighting, if you look at the total harmonic, the harmonic distortion spectrum, the amount of harmonics number 3, 5, 7 and 9 are high. Okay. Second is the adjustable speed drives, ASD. So ASD are widely used to control the speed of AC motor nowadays compared to the application of belts and pulleys in the 1970s. Okay, so this is the ASD input current, and this is its IHD, okay, IHD with motor operating at 45 Hz. So the harmonics value for 5 and 7 also high. Okay, this is for the personal computers, other sources, for example, the TV, aircon, laser printers. All this is the equipment that function as the sources for the harmonics in the electrical system. So you can see the harmonic distortion spectrum and also the waveform. And then we also have the electric furnace as the harmonic sources. So high power and high harmonic distortion devices in power system produce non-integer current harmonics during melting process. Okay, 5th and 7th harmonics are produced for electric furnace. Okay, and then we have AC-DC converters. If the number of converter or inverter pulses is P, then the order of harmonic current in AC side will be, so this one is the equation 4.20 NP plus minus 1. Okay, so effects of the harmonics. Some of the effects of the harmonics are disturbance to electric and electronic devices, and then higher losses because of harmonic current circulating in the power system that will increase the copper losses and indirectly will hitting the equipment such as generators and also the transformers. And then extra neutral current, okay, improper working of metering device, and also resonance problem. Okay, we will look one by one for the effects of the harmonics. The first one is the disturbance to the electric and electronic devices. So harmonics can cause disturbance in sensitive loads in power systems such as sensitive medical devices, control circuits, and computers. Control circuits that work on current and or voltage zero crossing are higher sensitivity to harmonics and may not work properly in the presence of the harmonics. So basically the zero crossing is here. Okay, the zero crossing at this point. At this point, okay. So higher losses, P losses equivalent to I squared times with the resistance. With the presence of harmonics, P losses harmonics equivalent to resistance times with the summation of the current harmonic squared. So excessive losses and torque fluctuation also appear in electric motors in the presence of harmonics because harmonic yields core losses and torque fluctuations. Only the fundamental component produce average torque in motors. Okay. Extra neutral current. So the presence of current harmonics IN, especially third harmonic in electrical power system, increase the neutral currents. Okay. So in three-phase four-wire system, in addition to the increasing size of the neutral wire due to higher harmonics currents, it also can cause overloading of power feeders, transformers, voltage distortion, and common mode noise. So typically phase current power supply, okay, you can see in this table. So the neutral current is 1.61 while the total phase current is 1. So have the extra neutral current. Okay, improper working of metering devices. So the presence of the current and voltage harmonics of more than 5% may lead to improper working of conventional metering devices that utilize induction watt-hour meters. Okay, it can cause interruption to the metering devices. And then resonance problem, current and voltage harmonics when passing through the power system or any another load may cause a resonant problems. Okay, so resonant problems is a physical effect in which several elements with specific values interact with each other, oscillating and amplifying a particular frequency. This amplification leads to higher energy consumption by forcing the system or some of its parts to work above their specifications. So if this resonance is not controlled, it can lead to the destruction of parts of the system or the entire system. So figure below shows a kind of resonance where the load has a resonant frequency close to the fifth harmonic. Okay. Next is about the voltage sags. Okay. Okay. Next is the voltage sags. So a voltage sags is a short duration, for example, 0.5 to 60 cycles, decrease in the RMS voltage magnitude, usually caused by a fault somewhere on the power system. Okay, so if you look onto this diagram, so this is a normal electrical power system diagram. Okay, if let's say an accident happened at point F1, okay, for example, accident happened in point F1, okay, where a car, this diagram, where a car crashed with the distribution pole and damaged the conductor system, so the entire electrical distribution system are interrupted. Okay, now as you can see here, there's an fault happens there. So first we have to understand the difference between an interruption and also a voltage sag. So this will happen a momentary interruptions. So an interruption is a complete loss of voltage, whereas a sag, this one is sag, voltage sag, is when the voltage drops below 90% of nominal. Interruption happens when a source side protective device opens a section of the circuit due to a fault condition as shown in the below bus figures. Okay, this one momentary interruption. In this case, the interruption is momentary, which lasts a few seconds. Okay. So while the other side, this one, these two parallel feeders momentary, these two parallel feeders will experience a voltage sag until the protective device clears the fault. Okay, so that is the difference between the interruption and also the voltage sag. Okay. So the magnitude of nominal voltage for the voltage sags case, it is around 0.1 per unit to 0.9 per unit. Okay, so the voltage drops will be below 90% of the nominal voltage. And then if the interruption is less than 0.1 per unit, because interruption is a complete loss of voltage. Okay, the duration for these voltage sags, we have three types. First one is the instantaneous, 0.5 cycles to 30 cycles. So one cycle equivalent to 16.7 milliseconds. Okay. Then momentary is 30 cycles to 3 seconds, and temporary is 3 seconds to 1 minute. So what is the sources of this voltage sags event? So any sudden increase in very big load will cause a V, the voltage sag. For instance, overcurrent. So we have motors, fault, switching. This is all the sources of voltage sags. Okay, so during starting for motors, so motors typically draw 6 to 8 times more current of their rated running. So motors may start and stop frequently, and common cause of voltage sags industrial facilities because they own large motors. Okay, so this is the starting motor example. So we have when motor starting, the current was nearly 3000 amp RMS during starting, and the voltage sagged to about 220 volt from 277 volt. Okay. The current line, the purple line is the current waveform, while the green line is the voltage waveform. Okay, so we look at the example 4. A stiff 14.4 kilovolt three-phase system serves a distribution line with an impedance of 1.2 plus J6 ohms. Okay, this one is the V line, Z line. Okay, this one is the Z line. Okay, and then if the voltage at the sending end remains 14.4 kilovolt, what is the voltage drop in the line due to a balanced three-phase load of 10 plus J5 ohms per phase? So this one is the Z load. So given variables, Z load is, impedance load is 10 plus J5 ohm, line impedance line is 1.2 plus J6 ohm, and V phase is 14.4 kilovolt divided by Z3. Then we calculate what is the line current. So line current equivalent to V phase over Z load plus Z line. So you get 529.598 with angle of negative 44.48 degree amperes. Okay. Okay, then you have to use this line current to find the voltage drop and load voltage. So the voltage drop is I line times Z line. So equivalent to 3.241 or with angle 34.21 degree kilovolt. Then you can get the V load is just V phase minus V drop. Then you can get 5.921 angle of negative 17.92 degree kilovolt for the V load. And then you have to find the voltage set, the percentage of voltage set by using this equation. Then you can get the voltage set percentage is 71.22%. Okay, so this is the typical voltage set tolerance referring to IEEE 1346 for different equipment. You can see there, for example, we have PLC. So upper range is 20 milliseconds, 75% or 0.75 per unit. And then average 260 milliseconds, 60%, and lower range 620 milliseconds with 45%. And so on. Okay. So next is about transients. So what is transients? Okay, this is one of the of the problem in power quality in power system. Okay, so transients are power quality disturbances that involve destructive high magnitudes of current and voltage, or even both. Okay. It may reach thousands of volts and amps, even in low voltage systems. However, such phenomenon only exists in a very short duration from less than 50 nanoseconds to as long as 50 milliseconds. And transients usually include abnormal frequency, which could reach to as high as 5 megahertz. Okay, that is uh, what is definition of transients. Okay, so if you refer to IEEE 1159 2019, transients defines with two types. Okay, first one is impulsive, the second one is oscillatory. Okay, so impulsive transients are described as a sudden non-power frequency changes in voltage, current, or both that is unidirectional in polarity. So an example such as lightning, removal of an inductive load, loose wiring, and other arcing events. So this impulsive transient happens in three lengths. First is the nanosecond, 5 nanosecond rise, last less than 50 nanosecond. And then we have microsecond, 1 microsecond rise, last 50 nanosecond to 1 millisecond. And milliseconds, 0.1 millisecond rise, last larger than 1 millisecond. Okay, so basically lightning happen. For example, the waveform is like this. Okay, so we have T, we have R here, then we have here, for example. Okay, so this is the lightning event. The current waveform if lightning event occurs, which indicate as a impulsive transient. Okay, the second one is the oscillatory transient. So oscillatory transient is described as a sudden non-power frequency changes in the voltage, current, or both that is bidirectional in polarity. Okay, for example, we have the event of back-to-back capacitor switching. Okay, so we have here. Okay, so this one is I and this one is T. So this one we call as oscillatory transients. Okay, they have three types in low frequency, less than 5 kilohertz, 0.3 to 50 milliseconds, 0 to 4 per unit, which is the capacitor switching, ferroresonance, transformer energization. And then we have medium frequency, 5 to 500 kilohertz, 20 microseconds, 0 to 8 per unit, back-to-back capacitor switching, cable switching, impulse response. And for the high frequency, 0.5 to 5 megahertz, 5 microseconds, 0 to 4 per unit, response of system to an impulsive transient. Okay. So this is the impacts on the loads. If transient happens, hard disk crash, power supply failure, component failure, silicon control rectifier or thyristor failure, circuit board failures, and process interruptions. Okay, so for the sources of this transient is we have distribution system, which are the lightning, switching operation, breakers, capacitors, fault clearing or breaker operations. While for customer system, we have lightning, arcing devices, starting and stopping motors, breaker operations, and capacitor switching. So the first one is lightning. So lightning is a huge temporary surge in voltage due to a lightning stroke terminating at a phase conductor, shield conductor, or any part of a system. So it can cause transients in the system from lightning. Okay, then because of the operation of nonlinear loads. Okay, so temporary overvoltage caused due to the frequency changes during the operation of the nonlinear loads in the electrical network. And then due to the motor starting. Okay, so voltage transient occurs whenever there is a sudden change in current in an inductive device. Electric motors, this occurs at startup when the contactors close and shut down when the contactors open. Okay, and then capacitor bank switching. So as we know that capacitors are used to provide reactive power Q to ensure power factor is unity. But one of the major drawbacks of this capacitor bank is building up of oscillatory transients as they are switched on. Okay, there are two power quality standards that we can refer to, which are the IEEE, which is the Institute of Electrical and Electronic Engineers, and also the IEC, International Electrotechnical Commission. So this is the IEEE 1159 1995 standard for the recommended practice for monitoring electric power quality. So we can refer to this standard, and also we can also refer to the IEC standard for the power quality system. Okay, with that, I thank you. So we have settled with chapter 4 and we will continue for chapter 5. Thank you. Assalamualaikum.